I would say we start then. I guess the rest is still in the weekend, but hopefully they will join us soon. Either way, we shortly start with a short recap about last Friday. So what have we done last Friday? We talked mainly about timing of digital circuits. So we had a look at example circuits, derived the logic functionality of the depicted circuit, decided which path is the longest by calculating the propagation delays of the according gates. And afterwards, we used the longest path, so the propagation delay of the combinatorial logic to calculate or to meet the setup time requirement. And this can be used then to calculate T periods, so the frequency we can run our circuit with. We also shortly discussed what hold time means and why both of those two requirements are necessary for digital circuits. And here you can see how you come from the period to the frequency for the first example. We did the exact same thing again and then ended up with calculating the mean time between failures. But before we dig into the mean time, are there any questions regarding setup, hold time, timing of digital circuits? No, there aren't. All right. Then afterwards, we calculated the mean time between failure. So just to mention, there are some numbers, which for example here, AS, which stands for attosecond, it is 10 to the power of minus 18. So be aware of that. But let's say for the examination, we will provide you with hints regarding that. All right. Then this is the formula for the mean time between failure. Don't be too scared of it. If it's like an examination question, we will provide this formula. But what you should know is like, what do the components of this formula mean? Like what is like T0, what is FD, FC, TR, and tau. So be aware of that. Then in order to get to the number of years, it's just plugging in the numbers. And here, for example, we had a description what tau r, TR means, so which is like the time a metastable event has to be resolved, so the available setting time without causing a metastable issue. Then we had a look what happens if we increase the time, so obviously the time between failures increases, and also showed that using some numbers. And this is like the second type of question you can expect, which is like, okay, now I have more than one device that runs. So what happens to the mean time between failure over all those devices? And maybe one of those devices do not run the whole day, but just some hours. So how do you handle that? And it's just dividing by the amount of complete hours that the device is running, or the devices are running. Next topic we discussed last Friday was logic implementation. So we had given some time of logic primitives. So we had multiple lookup tables of the size that they have 4 input signals, 1 output signal, 2 different types of flip-flop. One had additionally an additional set, so not only a clear signal, and this enabled us to do some optimizations, but first have a look at what happens if we want to implement this logic functionality A or B, C, D, E. And we want to do that with a flip-flop without a set signal first. So then we come to this result. So we need 2 lookup tables because we have like 5 input signals to that function, right? But we only have a for lookup table. So the first lookup table then gets 4 input signals, the second one gets 1. In that case, it's done the way that the first lookup table implements the AND operation and the second one the OR. And then we just feed the output to the flip-flop and it gets the according value stored. So now we come to the optimization. If we have a set signal, we can use this to represent A. So we only need one lookup table now that realizes the AND functionality, and the OR functionality of OR A can just be realized by setting the output register directly, which saved us one LUT, which can be now used for different functionality. And yeah, we can just pack through this optimization more logic on one FPGA. Then we started already with the next topic, which are FIFO implementations. So a buffer module that outputs the input in the order it came in, so first in, first out. And usually you use FIFOs if you have 2 modules running at different frequencies. In this case, module A runs at 500 megahertz and module B with 50 megahertz. So this means that module A produces much faster data than module B can receive this data. So you need some kind of buffering in between. And we also knew that module A does bursts of 500. So it sends 500 packets at a time, then makes a large enough break so that module B can receive all the data and then sends the next packet or packets. Okay, then we had a look, how do we dimension this FIFO? And in order to do that, it's a good idea to have a look at how much time does module A need until all the packets are sent. So this is just like knowing one packet needs 2 nanoseconds, which is like the period of the frequency. So at 1 clock period, 1 packet gets sent. And since we have a burst size of 500, we just multiply this number by 500, and we end up with thousands nanoseconds transmission time of 500 packets. So don't get confused that the burst size is 500 and the frequency is also like 500 megahertz. Then next step is to calculate, like, okay, module A needs so many seconds to, let's say, produce or send the data. In the same time, module B can already start receiving the data, and how many packets in the same time can module B receive? And so we more or less do just the same. Module B can receive 1 packet every 20 nanoseconds, and we have 1,000 nanoseconds that module A sends data, so we just divide 1,000 by 20, and then we know, okay, 50 packets can be received by module B, while module A is sending 500 packets. So now we have like a difference in between sent and received modules, which is 450 packets. So what do we do with those packets? Those packets, they need to be stored. And for that, we're gonna use a FIFO. Then we also already looked into what happens if module A does not work in a burst-sized manner. So what happens if module A continuously sends data out? So would it still be possible with a FIFO to enable that we don't have any data loss? And in theory, yes, but it would only be possible if we had infinite memory, which obviously is not the case. So be aware of that. If you have a module that's continuously produces data at a much higher frequency than the receiving one, a FIFO will not help you. So it's only useful if you have like a packet size of manner that you're gonna receive, or a burst size manner. All right, so then let's start with the next question, which is like what components and signals are required. All right, so the question is what components and signals are required to implement a circular FIFO. All right. Any ideas for that already? I'm gonna give you like 2 minutes. Does anyone know how to stop that beeping? Okay. Ah, perfect. Thank you very much. All right. I would say let's shortly have a look at how to implement a FIFO. And you first definitely need some kind of memory. So you could either use flip-flops or you could BRAM, because you want to store data, right? So some kind of storage element is needed. What storage element it is, more or less doesn't matter. It should be definitely one that is on chip, because your FIFO implementation should also run on the same frequency as your module or as your modules. And that's why either flip-flops or BRAM. So BRAM is like SRAM, right? But just in a block ordered manner, and this is the special term for FPGA SRAM that contains only data. Then we need like to know, okay, we have one sending, some writing module, and we have a reading module. So you need a read and a write pointer, so you know, okay, from which memory address do I need to write to, and from which address do I need to read from. And then I need to know when do I want to read or write. So I also need enable signals for those. And then the other important thing is like that we have some full and empty flags. So to know whether our module is full or empty. So in the end, you just end up with like something like this, which is like normally one such a thing is a packet, and you can get multiple packets, right? So this is like packet 0, packet 1, and so on. So usually you start up with this is your write pointer, this is your read pointer. So what do is like in the beginning it looks like this. You then have your write pointer here, you know, okay, I want to write packet 0, so I write it in there. Then let's assume like, okay, I add another packet, I want to add another packet. No, it's when? Okay, maybe let's start again. I write packet 0 in there, so next thing I need to do is like I need to increment the write pointer by 1 so that I know, okay, where do I want to write next. So next packet ends up here, and so on. So I increment this one again, now it points here. Then I write packet 2, and so on. Maybe in the meantime, module B, so the receiving one, wants to read some data. So first thing is like it reads data from here where the read pointer is pointing at. So it reads that data out, increments the read pointer, then it reads out this one, increments the read pointer. All right. So now there's just one packet left. So it reads out this one. Write pointer is already pointing here, right? And increments this one as well. And now you see, okay, both of those write pointers, both of the write and the read pointers are pointing to the same location. So now I know, okay, if they are exactly the same, then my FIFO is empty, and I accordingly set the empty flag. So just like how this in theory works like. Are there any questions? No. Okay. So now the big question is like, what kind of element, memory element would you use? So as said before, you have like two options. You have either flip-flops or you have the option to use SRAM or BRAM. And we have two kind of scenarios we want to look at. So this is like either we have a small FIFO or we have a large FIFO. And the question now is, would you use flip-flops or SRAM for small FIFOs? And what would you do for large FIFOs? Yeah, for the latch? Yeah. No, you don't. So a latch is like, or could be a building block of a flip-flop, right? And this is more or less a cross-coupled inverter, right? So a latch more or less is like something that looks like this. You have a inverter and then you have another inverter. I think we've seen that sometimes now, right? And this is not like a SRAM cell. A SRAM cell is like kind of also a cross-coupled inverter, but you get additionally like access transistors to read and write from them, right? So more think of it like you have different building blocks. You have latches, flip-flops, which are built up from latches, right? And you have SRAM cells, which is dedicated memory. And the main difference is there like that SRAM cells are packed in like an array manner. So they're not like widely distributed over your chip, but come in like array kind of structures with sense amplifiers to read them and so on. And a latch and also FIFOs, they don't need additional read sense amplifiers, so it's just like a different building block. Yeah. All right. Anyone who wants to answer the question? Why is that? All right. So the second part could make sense because then you have like a DRAM that you use and implement your FIFO inside the DRAM. That's something in theory you can definitely do. So usually you don't use DRAM for FIFO implementations on chip. So you could realize a FIFO using DRAM. That's not an issue and you could do that, but it's not what's done if you use it as a module in between different clock domains. Because like normally DRAM is something that is off chip, right? And now you have like two modules that want to communicate, but on chip. So then you would need to go off chip to the DRAM and then on chip again to the other module. So that's why you usually don't want to do this, right? So what you do instead is you want to use memory that is available on chip. And for that you either have flip-flops or you have SRAM. Now, so the question here is like, which one would you use flip-flops for and which one would you use SRAM for? It's exactly the other way around. Yeah, it's all right. But yeah, why is that? It's like a flip-flop is very suitable if you have just like a few bits or bytes, because SRAM is like, yeah, let's call it like too much, because SRAM usually comes, as I said before, in larger arrays. You need sense amplifiers for that, and this makes only sense if you have a certain amount of data you want to store. So think of it like SRAM is like more heavy and suitable for a lot of data, or more data than flip-flops. So here it definitely makes sense to use flip-flops. So there's also like something called distributed RAM, but I wouldn't go into that very much, but just to be aware of it. We also talked about LUTRAMs already a little bit. So this relates to using LUTRAMs for this case, but it's okay if you just remember we use flip-flops in this scenario. And for the large FIFO, we use SRAM because it allows us just to store multiple kilobyte of data. So we can maybe also think of it like from a different perspective. A flip-flop, if we have a look at it area-wise and compare how much area do I need to store 1 bit in a flip-flop and how much area do I need to store 1 bit in an SRAM cell, then the flip-flop is usually much larger than the SRAM cell. All right, then let's come to the fourth question, which is apart from just buffering data, so this is what we used flip-flop so far for, what is the advantage from a computational point of view if we use a FIFO for two different or two separate, two different processing modules? All right, I would say we have a look at the answer for this question. So the main advantage is like we have two modules, and normally if you don't have a FIFO in between those, then you can only operate them on the same frequency, meaning the one is producing data at the same rate, the other one can handle this data. So now the thing is, if we add a asynchronous FIFO in between, then the one module can run at a different frequency than the other one. And let's say one is more compute intensive, and if you can run this one on a faster frequency, then the overall end result is much faster available. So this is why we get a better performance out of it. And the other thing is like that the receiving module cannot block the sensor module due to missing back pressure mechanisms. And this means like, let's formulate it differently. If module B is busy doing stuff and cannot receive data from module A, it would directly block module A from creating data if there isn't a buffer in between, right? So module A needs to wait until module B is ready to receive data and then can continue processing as well. So if you then add a FIFO in between, then module B can do its thing, can be like not available to receive data, and module A in the meantime can still produce data, write it into the FIFO, and is not like back pressured, meaning like that it cannot compute on its own while module B is not being able to receive data. So yes, okay. So let's assume you have like a module A and a module B. And module A wants to send data to module B, right? But module B says to module A, no, I am not able to receive data, okay? Then module A cannot send data to module B because module B just says, no, I cannot receive. This means that module A is now stuck as well, right? Because module A wants to write data, but is not allowed to, because module B is like saying, no, I don't want to receive, and this is kind of like back pressuring to module A that it cannot send the data, and now module A is also just stuck and waits until module B finished its computation. And if you now add buffering in between here, then module B can still tell the buffer like, I don't can receive anything. Then the buffer says, okay, but still tells module A, I still have space, so just write data. And then module A can just continue also its task. And module B then would just read the data from the FIFO as soon as it's able to receive data. Yeah. Okay, so have you heard of a valid ready handshaking already? So what you usually do if you have like two modules communicating with each other and module A wants to send data to module B, then you have your data signals, and then you add some handshaking protocol to it. So what you also say is like module A tells module B if the data that is on that line is valid, and only if the data is valid, then module B should be taking this data. But what's also happening is like that module B is telling module A that it is ready to receive data. Because module A needs to know at what point in time module B says, okay, I've read your data, and it would only do that if it's ready. And such a handshaking protocol is like then this back pressure mechanism. Yeah. So back pressure is, yeah, I wouldn't call it like a mechanism, more or less, even if it's written on that slide. So it's like just that module B is back pressuring module A. Yeah. Yes? So let's assume we don't have like this back pressure mechanism here. Like we don't tell module A that module B is ready. Then what module A would just do is like it would just write data, say it's valid, and it would assume that module B is able to handle this data, right? And never is like doing this back pressuring and saying, I'm not ready. So this is then the assumption that module B is always able to receive data. And if that's not the case, then just the data that is sent is gone. It's just dropped. Yeah? Okay. Any other questions regarding this? No. Yeah, come again, please. Yeah, so you always go through the FIFO, right? So you always use it. And if module B is either saying I cannot receive, or is receiving at a much slower rate than module A produces data, then the FIFO will fill up. Yes. And then it's like a question, how do you dimension your FIFO? And this is what we have done before, thinking about, okay, what are the different rates? Module A is producing data and module B is receiving. And then decide, okay, our FIFO must be, let's say, 450 packets large. Okay, so if like the FIFO is full, right? Then either you also have like this handshaking protocol that allows the back pressuring. Then it will tell module A, so I'm not able to receive any more data. Please don't write to me. Or you just drop packets. All right, anything else? No, okay. Then that was it regarding FIFO implementations. So next topic is gonna be about a arithmetic logic unit. Let's see how do computers calculate and what do we need for it. So which operands, which operations do we want to have, and how do we build something like a ALU. So these are the questions at hand we're gonna have a look at for the next couple of minutes. So first thing is like briefly explain the purpose of every input and output signal, meaning that on the task sheet you'll find a figure depicting a processing unit, and it is labeled within an output signals. So briefly explain what you expect those signals mean, and also give an idea of how the functionality of those signals could be implemented. So how would you produce this data or those output signals I think we're gonna have a look at the first two questions for the next couple of minutes and then continue with the other ones. If you have any questions while answering one and two, please just ask. All right. I would say let's continue and see what the signals mean, and yeah, we will give a rough idea of how to implement those. So maybe first thing we can also notice is like that our ALU should do 4 different kind of operations. It should be able to do an addition, a subtraction, bitwise AND, and bitwise OR. So if we now have a look at our processing unit that is part of the ALU, right? Consists of an opcode that selects which operation do we want to do, and it consists of 2-bit. Why is that? We have like 4 operations we want to realize. To encode those in a binary fashion, we need 2 bits. Then we have A and B, which are like the input signals which we want to process. And for example, we want to add A and B or subtract A and B. And the result is then also 8-bit large and a C. And then we have a couple of additional, let's call it flags. We have like a carry, a overflow, a 0, and a negative flag. And what do they mean exactly? Let's have a look at this at the following slides. So these are the signals, A, B, and C. So as I said, A, B, the operand, C, the result. We have our opcode, so the operation. And now the interesting part, we have our carry flag, which is nothing else than the carry out of our MSB. So if we do a addition, then this is just the carry out of our adder, especially of the adder who's add the MSBs of the signals. And it is used for the unsigned addition and subtraction only. So notice here it's just for unsigned. And if we have signed addition and subtraction, we use the overflow flag. And this tells us whether we have an overflow of the signed result. So then there are 2 other flags which are 0. This is set if the result is 0, and the negative flag which is set if the result is negative. So these are like typically contained in a ALU. So most processors you look at, they gonna have like a status register you can also read out, and these gonna contain those flags, especially if you write like assembler, so assembly code. You probably gonna make use of especially the 0 or the negative flags in order to do some optimizations in your code. So now going one step further, how do we implement those now in hardware? So bitwise AND and OR. So this is like probably the easiest one, which is just a simple 8-bit logic operation. So we could use a lookup table, for example, for that one, or a simple AND or OR gate. For the addition and subtraction, so for the addition, I think you've already seen during the lecture a lot of adders. So one idea is like just, okay, we're gonna use a chain of full adders. So what exact kind of adder we're gonna use, never mind. And, but how are we gonna do a subtraction? So this, I guess, is the interesting part. So just remember that a minus b is exactly the same thing as a plus negative b. So we just need to make sure that we add a negative b, and how we realize that we're gonna see during this task as well. The carry is, yeah, kind of then easy if we already have a adder, and the carry is the carry of the MSB, then just use the carry out of the last full adder and copy paste this one as the carry. And the overflow, this is now like the interesting part. I hope you've already seen how you encode negative numbers. So usually the MSB of your negative number is set to 1 and 0 if it's positive. So the MSB indicates your sign, right? And when does now an overflow occur? And this happens if during the calculation the MSB toggles, meaning that if both operands have the same sign but the result have a different one. So if both operands, for example, are positive and your result is negative, then obviously during your calculation your sign mixed up. And also if you have two negative operands, then obviously your result is also wrong if the MSB toggles. Okay, and 0 is implemented like, okay, if there's any bit in the result not 0, so if there is a single 1, then the 0 flag is set. And for the negative one, as already mentioned, the MSB indicates the sign, and if the MSB is 1, then the negative flag can be directly set from that one. Questions? Not so far. Okay, then third question is, how can we now use a full adder to subtract two numbers? So what we want to do is a minus b, and as already mentioned, the first trick we're gonna do is like that we make an addition out of that subtraction and say, okay, we want to add a plus minus b. Now the question is, how do we get minus b? And minus b is nothing else. So if we want to have it in the 2's complement, the calculation rule is like that we take b, negate it, so make the negation, and add 1. So now the idea is like, in order to calculate a minus b, we do following. We keep a as it is, and then we calculate plus negative b, so the negation of b, plus 1. And one idea to get the negation of a signal is like using XOR. If we have a look at a XOR logic table, then this looks like this, right? And if we, let's say, split it here, so meaning that if A is 0, then it's just forwarding B, right? Then it's just like B. And if A is 1, then it's not B, and that's what we want, right? So the nice thing here is now that we can use A to select whether we want B or we want not B, right? And this is how we can use the XOR operation to select whether we want B or not B. And now the trick is, how do we simply add a plus 1? So if we have a full adder that we use, then a full adder always has a carry in. And remember the carry chain, the full adder chains we have, and the full adder for the LSB also has a carry-in signal, but most of the times this carry-in is 0 because you don't have a carry-in for normal addition for the LSB, right? Because there's no full adder before. But here the trick is we're just gonna use this carry-in and set it to 1. So we just have like the addition of 1 by that. And then coming from that, we just do this step and realize everything. So we add the XOR here and use the opcode to select whether we want to have the negation of B or not. So if we want to do the subtraction, then we set this one to 1. If not, then we just forward B. And also, if we have the subtraction in the opcode, we set the carry-in bit as well to get this +1. Question regarding this one. Everyone understood the idea how we have this come from a -b to the negation +1 thing, and how we use a full adder to realize this. So now the 4th question, how do we actually implement the output flags? So one way to reformulate this question, what is the logic function to realize the flag? I'm gonna give you like 2-3 minutes for this one. All right, so let's have a short look how you could realize that. So for the carry, once again, it's just like the output of the last full adder. And for the overflow, as said before, if the MSB of A and B are not the same for the output, then the overflow bit is set. So this tells us if we have a negative operand A and a negative operand B, and the result is positive, then we have an overflow. If we have a negative operand A, a negative operand B, but a positive operand C, then we also have an overflow. And for the 0, we just take every bit of C, or it together, and then take the negation of it. Because so the idea is like if one bit in C is 1, then this part here gets 1. But since we want to have 0, we just negate it, and we get the 0 flag. And for the negative, once more, it's just like the MSB of the result telling us whether the result is negative or positive. Okay, so next task is to draw a block diagram of it. And let's maybe phrase it like this. If you have a look already at those numbers here, then you can get a rough guess of like how the granularity of the block diagram should be. All right, I would say we make a break for like 10-12 minutes, and afterwards we're gonna discuss the result of this diagram. All right, so okay, then let's discuss the solution of drawing a block diagram. So this should look very familiar if we only have a look at the in and the outputs. So we have AB as inputs, C as our result. Here we have one opcode bit, here we have the other opcode bit. Then we have our flags, 0, negative, carry, and overflow. And now the question is like, what different modules do we need? How do we use them, connect them So maybe let's start with the first operation, which is a AND operation. So what we do is like we take input A and input B, feed those to the AND operation, right? And this is nothing else, so it could be just a large AND gate. It's probably not the best idea, and most of the chip vendors wouldn't provide you, I guess, with a such a high fan-in gate. But in theory, it could be just one AND gate, or you use multiple ones. And you do the same thing for the OR operation, right? You take the input A and B, forward it to the OR operation, and then you get 1 bit of output here. You have 2 times 8 input here, right? And then you have 1 output bit here and the other one here. And now the question is, which one do I forward to C? And this depends on the opcode. So for example, we just use the opcode bit 0 to select between AND and OR. So if we think of our opcode, we have bit 0 and bit 1. Then we use bit 0 to select, and if it is 0, we get a OR, and if it is a 1, we get a AND. All right. That's for AND and OR. Then we have another operation, which is addition and subtraction. And as we have seen before, we can just use a adder to realize this, and we use a 8-bit adder to realize that. So once again, we need to feed the inputs to the adder. So input A, input B. This is now the XOR we've seen before, right? So we use this XOR gate here to negate B if we want to do the subtraction. And this also depends on the opcode. So now if the opcode 0 is 1, we do the subtraction. Otherwise, we do the addition. Now the output of our adder is a 8-bit value. Either it's like the addition or the subtraction. And now we have another multiplexer here, which forwards this to the output C. And now we also need to select, okay, do we do a logic operation or do we do a addition or subtraction? And for this, we use the opcode 1. And if it's a 1, we do addition or subtraction. If it's 0, we do the logic operation. So don't be confused about this one. You could have come up with other solutions to it, right? So the mapping of opcode to the operations is completely your choice. You don't need to do it exactly like this. It's just like an idea we came up with. And then you need to, for example, calculate the 0 flag, which was nothing else than ORing all the output, the result bits together, which is done here. And we also need a negation of this one. So we have a not here, and we get our 0 bit. For the negative flag, it's very simple. We just take the MSB of the result and put it out as our negative flag. And then the carry is just the carry out of the MSB of our adder. We forward this to the output. And for the overflow detection, it's a bit more complicated. But if you remember, it's like either, let's start with this one here, like the MSBs of the input signals. I take both of these, and if the MSB of the result is negative, if the MSBs of the inputs are positive, then we get an overflow, or the other way around. If both of the inputs are negative and the MSB of the result is positive, or the result is positive, then we also get an overflow. So we also add the OR here because both situations apply for the overflow, and that's it. Yes? Yes? Okay, so this 0 here is bit 0 of the opcode, and this is bit 1 of the opcode. Yeah, all right. Any other questions? Okay, so now the question is, what is the delay? So we want also area and we want delay. So maybe we start with the delay first. So this is like the longest path, and we need to identify this one first. And any ideas which one is the longest path? You also have some numbers for the gates, for the adder, for AND and OR, for muxes. So there are numbers already. So which one is the longest path? So have you seen the unit GE before? No. Okay. Thought that maybe anyone would ask what does GE mean, but GE stands for gate equivalence. And this is like usually used more in ASIC implementations than in FPGA implementations. So the idea behind gate equivalence is that you make different technologies comparable. So let's imagine you have different vendors of your chip technologies, and they all provide you with different gates, right? But they all gonna provide you with the same logic functionalities. So they will provide you, so both vendors would provide you with an AND gate, with an OR gate, but the AND gate of vendor 1 looks different to the AND gate of vendor 2, has different properties. For example, has different area, has different delay. And this is why want to make your circuit comparable, even if you've implemented for a certain vendor. But if anyone wants to implement that on the technology of a different vendor, he probably also wants to know how would it perform on that technology. So you don't use like the actual numbers for the specific vendor you have used. So what you use instead is the gate equivalence. And this is just a, so what you do there is you pick one gate of that vendor. Usually that's like the NAND gate of that vendor. And this is like your baseline. And divide all the numbers by the numbers for that NAND gate. And then you end up with the gate equivalence. Yeah, yes. So yeah, what does better and not so good mean, right? It's a representation, but if you have like a higher gate equivalence, then also you have a higher area you need in the end. Or yeah, for the area, yes. Yeah. Mm-hmm. So it can be both. So what you usually have is like, for example, let's say we take delay of an AND gate and we take area of an AND gate. Or usually it's NAND. Let's make it like that it's NAND. So this is like the smallest gate you find in the technology. And then you, let's say, take the delay of I don't know, 3-input OR gate, okay? And then you divide this by the delay of this NAND gate. And then you end up with a delay in gate equivalence. And the same thing you can do for the area. So you have your area for this 3-input OR gate. Divide this by the area of the NAND, and you end up with the area in gate equivalence. Can you repeat that again? Okay, why do I divide that? That's a very good question, and it is done because let's assume you do this for one technology. Then you do X. Okay, maybe we do it differently. Let's say you get a number from vendor X. This is delay of your 3 input or of vendor A. And you get a delay of a 3 input or of vendor, let's call them vendor B, and this is vendor A. So then you have 2 different numbers. And you have like no idea how do they compare in that technology. But what you then do is like you divide it by the delay of the NAND gate in that technology. So this is like the delay of the NAND gate of vendor A. And then you get a rough feeling of like how fast is the 3 input OR actually in that technology, right? And the same thing for vendor B. And if you now want to compare those 2 vendors, then you see like, okay, the 3 input OR of this vendor is like faster than the 3 input OR of this one in relation to the fastest gate. Yeah, so let's say maybe this is not the 3 input gate then, but this is like the delay of your module, okay? You measure the delay of your module in that technology. And if you would do that, then you would also like measure like the delays that depend on that specific technology, right? And if you like divide it by the NAND, then you just cancel out all the technology-specific delays and get a better feeling of what is the actual delay of your module. Yeah. All right, so this is our longest path. It traverses through the XOR here, through our adder, then goes through the mux, all the way down through the NOT, through the AND, and through the OR to the overflow. So how large is that? This is just like then T XOR, T adder, T mux, T NOT, T AND, and T OR. You sum them up, and your result is then like 36.5 gate equivalents. Questions? No. Okay. So now the question, what is the area of our overall design? So we have our 8-bit AND, which is like 8 times the AND gate. And since you can calculate those 8 ANDs in parallel, you only get a delay of 1 AND here, just to be mentioned. And this is the same for OR and XOR. And then we add the area of all elements. So anyone has the question why we have 8 XORs? The reason behind that is that our input here is 8-bit large. So that is why we need 8 XOR gates actually here. We have 1 adder and we have 4 NOTs. This is just like counting them. So 1, 2, 3, 4. And then we get 2 ORs, 2 ANDs, and 2 muxes. So also just like counting, 2 muxes, 2 ANDs, 2 ORs. And if we sum that up, we end up with 181 gate equivalents. So this is for the area of the complete PU. Questions? Yeah. Yeah, it's like, so the question is, what is the area of our module? Yeah. Not just the longest path. Maybe this is a little bit confusing here. Yeah. But the area of the overall module. Yeah. All right. Then for the next 5 minutes, discuss whether this module you have seen is a arithmetic logic unit or not. All right, so maybe first thing we should think of before saying it is an ALU or it is not is like, what are the requirements to be an ALU? So what do you think? What operations do you need to be called an ALU? What is the minimal set of operations? So I've heard addition, that is true. Inversion, yes. And? Yeah. So we definitely need addition. We need inversion, and we need either a AND or a OR. And this is like the minimal set. And with those three things, you should be able to do all operations you need. So now the question is, our processing unit we have drawn before, is this actually an ALU? So what have we implemented? We have implemented an addition, right? So that's good. We also have subtraction. That's a plus, okay? We have implemented a AND. Yes. Have we implemented a NOT? No, we haven't. We don't have implemented a NOT. So there are NOT elements inside the circuitry, but it's not like an output, right? So if we go back one step to this slide, so we have the add operation forwarded to our output C, to the result. We have our AND operation forwarded. We even have an OR operation forwarded, but that's not necessary. And then the third thing would be like a NOT operation. But this path here does not contain any NOT operation. So yeah, if we could do something like input A is not C, then we would be happy. So I'm not entirely sure what the idea would be. So the idea is that you put in a negative number. B is an unsigned value, okay? So that would be addition with 0, right? And so 0 minus, yeah, okay? Then you would have calculated 0 minus A. So then your result is like a different one, right? Or 0 minus B you would have calculated, but then you have minus B. And if you convert minus B is then, okay, then you would convert it again, then you have B again. So then it's just like, so minus B is not the same thing as not B, right? No, it's all right. It's good that you play around and find different ways of thinking. So that's like what an engineer should do. Any other questions? Okay, as mentioned, we don't have an ALU. And I would say we make another, let's say, 5 minutes break until we dig into the next topic. Okay, then let's continue. Maybe one short remark. I think the door here is kind of broken, so please, when entering through the door on my right side, on your left, make sure that you really close it when you come in. Otherwise, it starts beeping, and probably me and all of you don't want that. So that would be nice. Then we're gonna start with the next topic. So we have now seen how do you build a ALU, right? And we kind of already know all the components. It's very simple, right? We have a AND gate, we would also need a NOT gate. We have seen how the data path looks like, how does the data traverse through that ALU unit. But what we haven't looked at it in specific is the adder. So how do we add two numbers? I think you've seen that already during the lecture, and we want to have a short recap. How do we add two numbers? And we have a task here at hand where Professor Calculus wants to build a 6-bit adder, but he only has the following components with him. So he only has a XOR gate and a 2-to-1 multiplexer. So this is like a different possibility how to implement a 6-bit adder. And our task is now to implement a 6-bit ripple carry adder. So hopefully you all remember how this should look like. And we are allowed to use as many XOR gates and multiplexers as we need. But we have the restriction that we cannot use any other logic gates or any other modules. So just those two. And just with those two things, we can already implement a ripple carry adder. What we have is like enough wires so that we can also connect the gates and the multiplexers. Okay. Maybe before I show that, a short recap of how to add two numbers. If we have A, B, and we want in the end A plus B. So if we add 0 and 0, so then the result is definitely 0, and we don't need a carry. If we add 0 and 1, the result is 1, and we also don't get a carry. Same thing if we have 1, 0, we get a 1, and our carry is 0 as well. And if we add 2 1s, then the result now is 0, and we get a carry. So this is like the basic idea behind adding two numbers. And now we can also extend this thing by what happens if we now have also a Cin. Then we have 1 here, right? So the sum is 1 as well, and we don't have a carry. Here we have 2 1s, means that the sum is 0 and we get a carry. And here we have 2 1s as well, means the sum is 0 and we get a carry. And here we have 3 1s, means the sum is 1 and we also get a carry. So this is like the logic of adding two numbers, right? Yes? Yeah, sorry, that's not that clear, right? C out, C in and C out. All right. So this is like basic addition of 2 bits. I hope you're already very familiar with that. And now the question is, how do we get to the sum? So this A plus B here is nothing else than Si. And what you see now, also depicted here on the right-hand side, is that Si is like a XOR gate of A XOR B, right? So this part here is like the XOR of A and B. And if we have now a carry in, so this is depicted here as Ci, then we have here like the inversion of an XOR, right? And as we learned, we can also use an XOR gate to select or to negate, or to make the negation. And so we can just use Cin XOR A XOR B, so A plus B, in order to get a result for Si. So then you have like A XOR B XOR C. All right. So what else do we need? We also need like the next carry. So this is like Ci plus 1 then. And how do we get there? So usually you have this formula here. And how do we come to this formula? I hope you already seen that during the lecture. But the easiest thing is like, okay, having a look at Cout, seeing where do I have a 1, which is the first one I see is this one, which is like then, okay, this one is 1 if A and B are both 1. So I say Cout is A and B. So now what's the next one? The next one is then like the this one here, and let me shortly have a look. All right. And the second thing is like, okay, now we see that if we write something like this, this is like the XOR, right, of A XOR B. And this only happens if Cin is 1. So this is like the right part, so A XOR B, and this happens only if Cin is also true. And lucky us, A and B, if A and B is true, then also the one here is set, so this is already covered by the AB we've placed there before, so this realizes this functionality. So this is just like one way to come to this function. There are also different ways, but that's like how you could think of it. And now we need to think of, okay, we don't have AND and OR gates, right? We only have XOR gates and multiplexers now that we can use. So maybe let's think of this a little bit in a different way. So maybe let's see and have a look at C plus 1 and see, yeah, how does this correspond to things? And we see here the green part, and we see that C plus 1 corresponds to C for this part here. And what else? C plus 1 corresponds to A or to B, doesn't matter for the rest of it. So if we now find a way how to select between those two options, then we only need to select between Ci or Bi, for example, and we also get Ci plus 1. And selecting is just like using a mux, right? So now the question is, how can we select this setting with an XOR gate? Because this is our restriction. We need a XOR operation for the selection. And if we have a closer look at this thing, then this part here, if I say now, so XOR is nothing else than it is 1 if the two inputs are different, right? So this exactly is this part here, where A XOR B is different. So if I then place A XOR B, then I get things like 0, 0, 1, 1, 1, 1, 0, 0. So now that's kind of nice, right? Because now I have like something I can use to select between the green and the blue output, right? So now I can then select either C1 if A XOR B is 1, or I use AI as the output if A XOR B is 0. So it's also on the slides. You don't need to draw that. So this is what I talked about. So exactly the same thing. And the nice thing is that this A XOR B now can be used as a switch for using A or C. So how does the resulting circuit then look like? This is how you can depict it. And what you see here is you have AI, BI now fed to the XOR, which selects us, the multiplexer. And in this case, we chose B to be forwarded to the output. Or in the other case, it's Ci, which then forms us our next carry, so our carry out. And for the sum, it's just another XOR with the carry in. And this is our result then in the end. Okay. Any questions? No. Okay. All right. So the next part is gonna be about the carry look ahead adder. So we have seen now how you could implement a ripple carry adder, and next part is then about the carry look ahead adder. So you should have already seen that during the lecture, and what what we want to calculate here now is a 16-bit addition, so not just a 8-bit addition, but now it's 16-bit. And we want to use the carry look ahead logic. And the task here at hand is to find expressions for pi, gi, and we define the carry look ahead logic, which is shown here in figure 9, so this part below here. So interesting here now is that we have already 4-bit carry look ahead adders implemented and use those 4-bit carry look ahead adders to build up the complete 16-bit adder. Now the question is how do we get P0, G0, Pi, G1, P2, G2, and how do we use those to form Cout? So this is going to be the question until the break, and we're going to discuss the results of it after lunch, so at 14 o'clock. So if you have any questions, please ask. Otherwise, this is the task for now. So maybe as a short recap for from the lecture, how do you calculate P, GI, P out, and so on. So I would recommend that you go through the slides now again and have a look at what this means and how to use it and what it does. So Pi is like the propagate, Gi is like the generate. So instead of, so we find a different way for generating the carry, right? So instead of building the carry and then passing it on through a long chain through all the adders, we want to find a way how to represent the carry without this long chain, dependency chain. So what we do instead is we say, okay, either we know as a processing element we generate a carry, or we know we propagate the carry. So instead of waiting until the previous module already gives us its carry, we say, I don't care whether you already gave me one, I just tell the carry look ahead logic whether I propagate or whether I generate a carry by myself. And how do I do that? So if we have a look here again, when do I generate a carry? It's just like if A and B are both 1, then I would generate a carry independently of the Cin. And now the question is when do I propagate? Yeah, I propagate if one of my inputs are already 1, because what would happen if I would have a Cin and one of my inputs would already be 1? I would just create a carry, and that is why propagate is then A XOR B. All right, so you can still continue, but otherwise we see each other at 2 again.